Hello everyone and welcome. My name is Jason Gregerson and in this video we're going to cover higher order linear differential equations. Now every higher order linear differential equation can be rewritten in this form where we have some function of t times the nth derivative of x plus another function of t to the n minus 1 derivative, so on and so forth, down to some function of t times the first derivative plus some function of t times x equals some function of t. So every linear differential equation can be written in this form. Now it's linear because we can represent this equation as some operator acting on our dependent variable equal to some function of our independent variable, and this would be linear if this operator L satisfies the conditions of linearity. So in other words, where L of some constant times a function plus some constant times another function is equal to the constant times L of x plus the constant times L of y. So this would be true in this case alpha and our beta are constants. And here x and y are our functions of the independent variable t. So every higher order linear differential equation can be written in this general form, or an operator form as L of x equals f of t, where L is a linear operator. Now let's look at a specific example. In this example, we have x double prime plus 2x prime minus 3x equals 0. So first, we're going to write this in operator form. If I let L equal the operator that takes the second derivative of something plus 2 times the derivative of something minus 3 times something, if that's my L, and I let my function f of t be 0 in this case, right, then we would have L of x equals f of t. And there's actually two special things about this specific higher order linear differential equation. The first is that the differential equation has constant coefficients. So in general, it could be linear if the coefficients to x and its derivatives are functions of t, but those are actually very hard to solve, and so in this course we're going to focus on linear differential equations that have constant coefficients. The other thing we'll notice in the specific example is that the right-hand side, or f of t, was actually equal to 0. In this case, our differential equation has an extra classification. It is homogeneous. So a homogeneous differential equation has the form L of x equals 0. And we'll start by learning how to solve linear homogeneous differential equations, and then we'll move on to linear non-homogeneous differential equations. Now consider the two functions. x1 is some function of t, and it happens to be e to the negative 3t. x2 is some other function of t, happens to be e to the t. Now, x1 is a solution to the differential equation if L of x1 is actually equal to 0. That's what it means for us to plug in this function of the differential equation. So, using our notation, if I looked at L of x1, that would be me applying this operator to my function. I would have the second derivative of e to the negative 3t plus 2 times the derivative of e to the negative 3t minus 3 times e to the negative 3t. And our hope is that this is equal to 0, and now we'll calculate these values and see if it is. So if I take the derivative of e to the negative 3t, the result is e to the negative 3t, but the chain rule will give me an extra factor of negative 3 out front. Taking the second derivative, I'll get a second factor of negative 3, so the second derivative is equal to 9e to the negative 3t, plus 2 times the derivative of e to the negative 3t, which in this case would be negative 6e to the negative 3t. And lastly, we have minus 3 times e to the negative 3t. As we see, we have 9 of these, minus 6 minus 3, that is going to equal 0. So it looks like x1 is a solution to the differential equation. And we could further on go ahead and show that x2 is also a solution, but for now we're just going to state that as fact. So it turns out x1 and x2 are both solutions to the differential equation. Now, because we know that L is a linear operator, we also know that L of some constant times our first solution plus some constant times our second solution. Because L is linear, we can use the properties of linearity to show that this statement is true. And if e to the negative t is a solution, then L of e to the negative 3t is equal to 0. And if e to the t is a solution, then L of et is equal to 0. And a constant times 0 plus a constant times 0 is equal to 0, which tells us that this is also a solution to the homogeneous equation. So, for a homogeneous linear differential equation with constant coefficients, because it's linear, we know that any multiple of a solution is also a solution, and the sum of solutions are also solutions. This means we can form a general solution to be C1 e to the negative 3t plus C2 e to the t, because any linear combination of our two solutions is also a solution. Or more generally, we'll say that for an nth order differential equation, the general solution will have the form of C1 times the first solution plus C2 times the second solution plus dot 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 plus Cn times the nth solution. And for an nth order differential equation, we'll have these n solutions in our general solution. Of course, the big question we still have is, how do we actually find these solutions, the x1, the x2 to xn? In our first example, we were given x1, x2. How would we find those? Well, to think about this, we might recall that there are really only two ways we solve differential equations. We either manipulate the equation algebraically and integrate, so manipulate and integrate, or two, we make an inspired guess. An inspired guess at the form of our solution, and then we plug it in to determine the missing parameters. And that's actually the technique we're going to use here for our higher order linear differential equations. So here's our solution technique. So we'll use our solution technique on this differential equation, x double prime minus 4x prime minus 5x equals 0. So our first step is to assume a form with a solution. We'll take a guess. Now, it's not any random guess here, it's a somewhat educated guess. The idea here we have some function, and we're going to take its derivative and its second derivative, and we're going to somehow combine them to get 0. But if I guessed my solution was x cubed, well, then the derivative would be 3x squared, and the second derivative would be 6x, but I can't combine these types of functions together and have it simplify. So what I need is a function whose derivatives look like the original function. And that makes me think of an exponential. So I'm going to assume my solution looks like e to the rt, like an exponential with some parameter in it. Now, if I assume my solution has that form, then the derivative would look like r e to the rt, because r is just some constant. And the second derivative would then look like r squared e to the rt. Now, if I plug these values into my differential equation, I'll have x double prime, which is r squared e to the rt, minus 4 times x prime, which is r e to the rt, minus 5 times x, which is e to the rt, and this is supposed to be equal to 0. Now, because e to the rt is an exponential and always is never equal to 0, I can actually divide through by e to the rt. When I do that, I'll get r squared minus 4r minus 5 equals 0. Now this equation, this polynomial equation, we're going to call our auxiliary equation. This is going to be our auxiliary equation. And what's special here is that x equals e to the rt, our guess here, is a solution to the differential equations if r is a solution to the auxiliary equation. So this lets us solve the auxiliary equation to find the right values of r to make our guess actually work. Now in this specific case, I have a polynomial which I could factor into r minus 5 and r plus 1. that tells me that r is equal to 5 and r is equal to -1. So that means my solutions, one solution would be e to the 5t, and another solution would be e to the -t. And so now I have my x1 and x2, and I can form my general solution, which would be c1 e to the 5t plus c2 e to the -t. So once I find x1, x2, I know my general solution is any linear combination of x1 and x2. And so my steps are: assume the solution has the form x equals rt, plug that guess in the differential equation to generate my auxiliary equation. Step 3 is to solve that for r, and then I can form my final solution. All right, that concludes this video. Thanks for your time.